In our last two videos, we learned about enantiomers, molecules that contain a chiral carbon or a chiral center. In this video, we'll learn about molecules that have more than one chiral center. We'll start with this example of a molecule with two chiral carbons. Each of these carbons is a chiral carbon or a chiral center, and if you apply the Kahn-Ingold-Prelog rules we learned in the last video, you'll find that each of these carbons has the S designation. First, let's draw the enantiomer of this compound. Just as with compounds that have only one chiral carbon, here to draw the enantiomer, we'll draw the mirror image. In the enantiomer, the mirror image, the two chiral carbons will now have the R stereochemical designation. So in the enantiomer, both stereocenters, both chiral carbons, have the opposite configuration as in our original structure. We can also draw the isomer where only one of the two chiral carbons has changed configuration. And here I'll draw the case where the left carbon is now an R stereocenter and the right carbon remains unchanged. Now in this structure, we have two chiral centers. One is inverted, but the other is the same as in the original structure. So comparing the two structures on the left, the two black structures, these are called diastereomers. This molecule on the bottom now also has an enantiomer. So we can draw its mirror image. And in its mirror image, both chiral carbons will be inverted. The two structures on the bottom here are enantiomers of one another. Now if we compare this last structure on the bottom right to the one above it, these two structures in blue, we see that the bottom structure has one stereocenter that's unchanged from the top structure and one that's been inverted. So the relationship between these two structures is diastereomers. In fact, the relationship between the corner structures in this graphic is also diastereomers. The top left structure and the bottom right structure also have one stereocenter that's unchanged and one that's been inverted, and so they are diastereomers. So when we have more than one chiral center, we can have enantiomers and diastereomers. And a diastereomer is a stereoisomer that is not a mirror image. We draw a diastereomer by changing some, but not all of the stereocenters, as we did above. An enantiomer is a stereoisomer that has opposite chirality at all of the stereocenters. When we have two stereocenters, there are four possible stereoisomers. When we have more than two stereocenters, the number of stereoisomers possible is defined as 2 to the number of stereocenters. Let's try a concept check. Draw a diastereomer for each of the compounds shown. To do this, we just need to remember that a diastereomer has some, but not all, of the stereocenters inverted. So if we have a structure with two chiral carbons, to draw the diastereomer, we'll leave one carbon the same and invert the stereochemistry of the other carbon. To invert the stereochemistry, that just means I need to change it from R to S or S to R. And the easiest way to do this is to exchange the position of two groups on that carbon. On the first structure, I'll invert the left carbon. I'll redraw everything on the right as it is, and then for the left carbon, I'll switch the hydrogen and the CO2H, the carboxylic acid. I could have also chosen to leave the left carbon untouched and invert the stereochemistry on the right-hand carbon, and so I'll draw that diastereomer here in red. For the second structure, I'll first invert the stereocenter with the chlorine. To do that, I'll simply change the dashed line to a wedge. Remember that for skeletal line drawings, that's the same as exchanging the chlorine and the hydrogen that's not drawn in. I can also invert the stereochemistry of the carbon bearing the alcohol by switching the alcohol from a wedge to a dash. And notice here that what we've done in drawing the diastereomers of the trans disubstituted cyclopentane is to draw the two cis disubstituted cyclopentanes. So the trans and cis stereoisomers are diastereomers. They're stereoisomers that are not mirror images. Finally, in the last example, I can invert the left carbon by exchanging the bromine and the fluorine. I'll do that in blue. Or I can invert the right carbon by exchanging the methyl group and the alcohol. I'll draw that one in red. The last piece to note here is that the two structures we drew for the first example are actually the same compound. If you take a look at those, we inverted first the left stereocenter and then the right stereocenter, and that gave us the same structure, it's just flipped. And this particular structure belongs to a class of molecules called mesocompounds, and that's what we'll learn about in the next video.